Okay, so there's some interruption in the previous video. That's why I'm continuing from where we stopped. So just to reiterate what we have been doing, the interrupt vector controller is something which we have to configure correctly to make use of an interrupt. And we discussed here, some of them are predefined, some of them like 32 options are for us to configure. The first step is, of course, you just need to identify the IRQ number. So the IRQ number will give you the bit position for the set enable register. Suppose you want to enable the port A as GPIO, you go and set the bit number 30 in the set enable register to 1. That enables the interrupt. Moment you do that, you have to go and make the priority for the port A. So for that, basically you need to again see the IRQ number, then go back to this formula. So 8 into IRQ in this case is 30 mod 4 plus 6. You get accordingly the corresponding bit number, and those two bits in which register. So that's the interesting part, right? Here the NBIC IPR 7. So NBIC IPR 7 is the register that you should look at, and the bit position is given by this formula. The corresponding two bits you set accordingly. So 0, 0 you set, that is the highest priority. 1, 1 you set, that's the lowest priority you can set. So the moment you do that, you have enabled the interrupt in that particular basically that particular option. It can be GPIO, SPI, or whatever, right? The moment you enable that, the interrupt is enabled, but then you need to set the priority. For that, you need to go and set the NBIC IPR register. And moment you did that, you made the priority also. The rest, NBIC will take care of. The rest, what you need to do, just think what you need to do. So configuration part is done. Now what you need to do is go and write the function, the interrupt routine that you want. Where you will write, that's an interesting question. So that I will show you where you will write. But that the pointer to that particular thing, interrupt service routine will be in one of these locations, from 0000040 all the way up to 000000 BC. Okay. Now let's do more of understanding what happens when an interrupt occurs. So as we know that CPU typically is executing its main program. So when an interrupt occurs, what happens? The first thing that CPU does is it saves the current context. So the program counter has to be saved, because the program counter will go to the address of the address of the interrupt service routine will be occupied in the program counter, right? Then only the interrupt service routine can be executed, right? Because in a CPU, all it cares is program counter. Whatever address is there in the program counter, the corresponding code will be executed. So when main program is executed, the lines, the addresses of the main program will come in the program counter. Moment an interrupt comes, the interrupt service routine address will come in the program counter. So, but before doing that, it needs the content of the program counter, and it needs to save certain registers. So if you go back to some of our previous lectures, I already told which registers to use in functions, which registers not to use in functions, and so on. But anyway, in the case of an interrupt, registers R0 to R3, R0, R1, R2, R3, register 12, and then program counter, program status register, and link register are all saved. And where does it get saved? Obviously, stack. Stack is the front. So it does for you. You don't have to do anything at all. The moment interrupt comes, network interrupt control register will help. That person will actually save all the context, program counter, registers, etc. to the stack, and then only the next step will be occurring. So that's a beauty. You don't have to get troubled much. So this is the first step. Then CPU grabs, or rather program counter will get the address of the interrupt service handler or routine from the vector table. Of course, again, NBIC is your friend here. It will take care of, and it goes and executes that particular interrupt service handler. You have to do that. The interrupt service handler by default is blank. You have to, I will show you that actually. So by default it is blank. You have to go and fill that, and it executes whatever is there inside that. It executes. Moment it is executed, you have to actually, the last line of the interrupt service handle, if you are doing it in assembly language, it has to be BXLR, branch to LR, because then only it can come back to the program, right? So that you have to do, and moment you do that, so all these are taken care, you don't have to worry anything, except that BXLR you have to add that line of code. Moment you do that, the CPU restores, or rather the NBIC restores from stack whatever it was saved at this point, and it behaves like nothing has happened and executes the remaining of the main program. So main program is the main objective of any CPU program, any microprocessor program. It keeps on executing that till the time it finds an interrupt. The moment the interrupt is triggered, if it is not a system interrupt, everything else will be handled by the NBIC. The NBIC prioritizes it, everything it does. It saves the content or context at that particular time for the main program, basically all the registers plus the program counter, including the program counter. In fact, program counter is a register. So all the registers are saved to stack. Then it goes and executes the interrupt service routine. The moment it executes the interrupt service routine, all the context is stored back from stack to the normalcy, and it keeps on executing the main program. So main program, interrupt, again back to main program. Okay. Now let's see in more detail, more engineering way of looking at it. So this is how a very illustrative case again. I'm just keeping it simple for you. So the x-axis here is the time, and obviously if there is no interrupt, the main program is what it executes all the time. There's no doubt about it. I'm just showing you a stack pointer illustration here. So somewhere here is a stack pointer. It's ready to start filling from here. So it is stack pointer is basically having the address of this location. And then this is our friend, the NBIC registers, the enable register, the active register, the pending register, the priority register. You can actually see this in the Keel software also. I'll show you. But of course, since no hardware is there, we cannot really run any code, but I'll just show you how it happens. Okay, so these registers, I'm just giving some example. This will be 0 to 32, but I'm only showing 3 to 7 here. This will be 0th register to 31st register, right? If you want to put all the registers into the picture. But let's assume we only have these 5 registers. And I'm just highlighting this in yellow shade because this is the interrupt I want to execute. So interrupt number 5. It may be associated with SPI 0. It may be associated with GPI 0. So I'm just giving an illustrative example, that's all. So this is interrupt number 3, 4, 5, 6, 7. And then correspondingly, these are the current status of the enable register, active register, and so on. So in this case, only interrupt to 5 is enabled. Others are all 0, correct? So if you see enable register, 7 is 0, 6 is 0, 4 is 0, 3 is 0. So even if interrupt comes in 3, 4, 6, and 7, nothing will happen because we have not enabled that register. Here 5 is enabled. So if some interrupt comes in 5, it will get enabled. Okay, and then I'm just giving some illustration here. The priorities for these registers or these interrupts rather are also here. So interrupt number 3 is having priority 9, interrupt 4 is having priority 8, 5 is having 4, 6 is having 5, and 7 is having 2. So out of all these 5 registers, of course, interrupt number 7 has the highest priority. Then it is interrupt number 5, then interrupt number 6, interrupt number 4, and interrupt number 9. So that's the thing. So currently, of course, only interrupt number 5 is enabled. So I don't have to worry about priority at this point of time. Suppose main program is executing at some point of time, our friend interrupt 5 comes. So it is coming from, let's say, GPIO. It triggers something, let's say photodiode got on because light. Then it triggers an interrupt. It reflects as interrupt number 5 suddenly. And then this is the interesting part, right? There is something happening by the NBIC. So NBIC looks at this and finds that no other registers are enabled and the priority is anyway 4 for it. That's the only thing. There's no pending interrupt happening. So it goes and starts executing. So first step is to make this register. So this is what done by NBIC. You are not doing anything. Only thing that you are doing is this enable register, you have to make it 1 and then priority you have to give. That's all. We already discussed about that. The moment this interrupt 5 comes and NBIC feels it's ready to be executed, it puts it into pending status. So you can see, you can observe this particular register. You see that it is set to 1. Okay? Same time, as we discussed, some stacking operation is happening. So stacking basically saves the current context of the main program to stack. So this is what exactly happens. So some stacking, and then if you see over here, all these registers, that's actually part of main program, right? The status at the end of this particular code or line of code, that's where the interrupt is coming. So this particular position, the status register, the program counter, the link register, R12, R3, R2, R1, R0, these are saved to the stack, and of course the stack pointer moved from here to here because all these are available in the stack now. So this is important, and you can ask me why only these set of registers. There's no specific reason, but this is how the vendor is giving us. So program counter, link register definitely need to be saved. So those, in fact, status register also, this needs to be saved. Out of these 5 registers are taken maybe for some reason because these registers are not basically useful in subroutine, so they are updated or put into stack. But you can ignore all this. So what happens actually is at this point, a stacking operation will happen and all these contents will get updated in the stack. Okay, so you're preserving these contents in the stack. Once that is done, the next step is basically it will go and execute the interrupt service routine corresponding to interrupt number 5, and from where the address will come, it will be in that table, vector table. You have to go and see. So you have to write inside. So this is not magic. You have to write inside that address location whatever you want to write, that interrupt service routine, and that interrupt service routine will get executed. And you can see, if you see these started registers, the pending will go to active. Now this means that the 5th interrupt is getting executed, or the interrupt service routine corresponding to interrupt number 5 is getting executed. That's what you're going to see over here. And the moment you're done with that, the last statement, as I said, should be BXLR. And that means the moment the interrupt service routine sees this, the control will be transferred again to the NBIC. And what NBIC does next is something known as unstacking. That is nothing but reversal of operation of stacking. That means all these operations that we are going to see over here will be reversed. That means R0 will go to R0, R1 will go to R1, R2 will go to R2, and so on. So it will be cleared. And then, of course, active register will also get cleared. And then, as next step, the moment that happens, it goes back exactly where it ended. It goes back and continues with the main program. So that is the beauty. So this is what happens exactly. Main program, interrupt happens, it goes for stacking, then it executes what is the content of that service routine. This statement happens and stacking happens, it goes back to the main program and executes. Absolutely perfect. And you have to do something. Yes, 2 things. Set the register accordingly. You have to enable the corresponding interrupts and get the priority correct. But these 2 are actually done. Rest everything is done by your friend, which is NBIC. Imagine the easiness with which you are doing interrupt nowadays. Moving forward, of course, the stack pointer will go back up to SP, the original location after the. Now this is a complicated case because you can think of this something like you are already executing an interrupt and suddenly another interrupt comes, which is very usual, right? Because our system is very complex. An embedded system you can think of has so many interrupts coming tup like that together. So, but then something has to be done. Let's see that. So let's see from the previous case. So main program interrupt 5 came, some stacking happened, and interrupt 5 service routine is currently being executed. Okay, so if you see here, so here I made a change from the previous case. I enabled this 7 also, and its priority was already 2, correct? So suddenly when interrupt service 5 was executed, this active register will be showing 1 against 5. At the same time, suddenly an interrupt 7 happens. Okay, so the CPU or the core is executing the service routine corresponding to interrupt number 5. At that point, interrupt 7 happened. Now there is a problem. So NBIC receives this, so it puts it to pending. So 7 is pending now. But then if you see here, the priority for 7 is higher than 5. Oh my God. So NBIC says, okay, CPU, please wait. A higher priority interrupt has come. So you have to stop executing the lower priority interrupt because you have to execute a higher priority interrupt. So that happens. That happens actually, and what exactly happens is you do another stacking. Okay, so remember this, after this stacking, all these contents from the main program is already there. So R0 is the R0 of main program, R1 is R1 of main program, so on. PC is PC of main program, whatever address here. Right? So now what happens? Oh my God. So there's a problem here. The problem here is, again, and one more stacking has to be happening, because there is some content for R0 to R1 to R3, R12, everything here also. So that will be stacked again. So you do that stacking. So this new content will be the content from ISR 5. Okay, whatever the status register at the point of ISR 5 is actually this one. This one is for the main program. Okay, and stack pointer has moved here now. So this stacking has happened. And then you see over here, active register is still here 1, and this is pending. But the moment this stacking happens, it is ready to get executed the interrupt service routine corresponding to 7. Okay, so moment you do that, interrupt service routine 7 is executed, you move 7 to active and 5 to pending, because 5 was getting executed, then suddenly 7 came. So now 7 is higher priority, so 7 will be executed, so it becomes active, this becomes pending. When you have 7 pending, and this can go on, another interrupt can come, then you again see priority, so it can go. That's why nested, the name nested in interrupt vector controller, that's why the name. Okay, so the moment that happens, this gets executed, that is done, this is done, then again that BXLR statement will come after that the unstacking will happen. So this entire thing will get recovered, right? So that is done, and now you can see over here, this is almost done, unstacking is done. ISR 5, once moment unstacking is done, it can start executing ISR 5. This is cleared, 7 is cleared because it's done. And again BXLR will come, another unstacking will come where this will get unstacked, and then this will be going back to the main program. So this is an interesting case where a main program was executed, suddenly an interrupt 5 happens. So stacking happened, ISR 5 was getting executed, but suddenly in between interrupt 7 comes. But then NBIC finds that interrupt 7 has a higher priority compared to 5. So obviously it has to be executed first. So it goes and execute ISR 7. Before that, it does the stacking. Moment it is done and stacking happens, it executes the remaining part, not from scratch, of course, because the status is already unstacked. So the remaining part of ISR 5 is executed, then again it unstacks, and then remaining part of the main program is executed. That is the beauty. Now you can ask me, this can be another case where this interrupt 7 which happens here, which is a lower priority interrupt. So main program was executing, interrupt 5 happened, and it is executing interrupt service routine corresponding to interrupt 5. But then interrupt 3 happened. But then NBIC see, oh okay, so it's a small change here, good. It's like a live class, so this has to be 1, otherwise it will not work. Okay, so I'll just go back up. So this is 1. So this interrupt has come, but that has a very high, lower priority compared to 4. So there is no need to disrupt. Let 5 happens, 5 completes. So 5 completes, the moment 5 completes, unstacking happens, but it will not go to main because this is already moved to pending. Okay, so let me just put that way so that it's easy for you to understand. And this is the active, right? That's a. Sometimes it's good so that you will also understand. So this is what it was active at this point, and then this is pending, it will be put to pending, and once moment it executes, it will unstack and then it will stack again. This will be happening and then it will unstack, it comes back to me. So here it didn't happen in between because interrupt service or interrupt 3 is having lower priority. So this is 4, so that is highest compared to 3. 3 is only having 9. So that is why it waits for full execution of this before this guy. Oh, so many errors. I'm sorry. Sorry. This is 3. Okay, that's what happens when you copy paste, right? But anyway, it's good for you because you'll understand. So interrupt service routine to 3 will execute and it goes. So main program, interrupt 5, its service routine, it fully executes, but suddenly interrupt 3 has happened, but it will wait for ISR 5 to complete. Then it comes back here, executes, comes back to main program, executes the remaining. So this is two interesting cases, but again, this can go in nested, and it becomes complicated. But fortunately for you, everything will be taken care of by NBIC. And you only have to take care of, as again repeat it, these two registers. Please be careful. You have to do it, this register and this register. Okay? So moving on, is this really necessary? You are actually doing a stacking and you are doing an unstacking. But is that necessary? You really don't need to do this because it's already there in the stack, right? You don't need to do anything new to the stack. The main program content is already there in stack. So all you need to do is you go and execute this guy suddenly, right? That's what you need to do because it's already saved. So that's why you do a compressed operation here, and that's what referred to as tail chaining in the microprocessor world. Okay? You don't need to do a stacking and unstacking because one interrupt will be executed only after completion of the other interrupt, and then you can do something known as tail chaining, which will be much faster operation. So compared to here, it's much longer. You can see over time it is stretched out. Okay, so we are done. So just to reiterate, so interrupt is your friend because otherwise you have to do the tedious job of polling, and that's not very friendly and not very good. Interrupt will help you. And if you allow me to go back to this slide, I think this slide will help. This slide, right? Some interrupts are hardwired system interrupts. Some interrupts you can actually prioritize, and these are your friends. And all these 32 interrupts are given from outside, and this vector table will help to see where is the address location. And you have to do two jobs. One is actually to set up the enable register so that the corresponding interrupt is enabled, and of course give the priority. And let me quickly illustrate this, okay, so that you are very clear. So again, go back to this and just simple program. This will work in actual case, but here it will not work because it's a simulation. What I'm actually trying to do is I'm trying to access some area which is read only. Somewhere around E, I think it is at this reserved region. So I'll just give you some examples. This region is some location which is reserved region, which I am not allowed to write to. So what I'm trying here over is to write to that location. Okay, write the content of R0. So this is not complete yet. So let me just put some. We're doing it together. I just purposefully did it instead of some value. Okay, some value here. I want to write to this location, and it is not allowed. So what happens is I load R0 with this value, R4 with this address, and store the content to this address, and it will create a hard form because it is a non-accessible location. And typically what happens is go to a handler named hard forward handler and executes whatever you write over here. I have not written anything here, but just a B loop B, so it stays here. But unfortunately, I can't simulate it because this you need a real hardware. So maybe next week sometime I will get the hardware and do it for you. And the moment you're back in, if you have hardware with you, the Freedom board with you, you can try it out. If not, when you come back to IIT Palakkad, you should definitely try this. So let me just compile it. And in fact, lab exercise after GPIO is in fact this. So you'll be definitely doing this. And now let's debug. Okay, so now I want to really point out something. So this is what it starts, and you see reset handler is where it starts. Where is it all defined? I'm just scrolling, and you might have never seen this before, even though you used it many times. So you see here, the stack size is defined here. So some size for the stack, and this is the space for it. Then heap size is next, and then this is the vector, the same table that we are seeing over here. Okay, it is already defined for you. So it starts with the initial stack pointer. Okay, So I just go back here for reference, initial stack pointer, then the program counter and so on. So the program counter, instead of that, as I said, it's a reset handler because I want to start from the reset handler, and it is a reset handler where you have filled something. So when the program, or when you press the reset button, or when you start the board, it goes to the initialization of stack pointer, and that is this guy. Okay, so it will get executed, okay, this label. So it gets executed all these, and then it will come to reset handler, and it goes to reset handler. That's what we were seeing earlier. And then the NMI handler, hard fold handler, that's a name. So you see here all these. So hard fold handler and so on till SysTick handler is system defined. And this is where our prioritizable interrupt starts, or MBIC interrupt starts. Same, exactly same, whatever we are seeing over here is already predefined for you, and the last is our port A, port B. So if you want to write something, you go back and write in this particular routine. And where is it defined? Let's go and see. Reset handler, we already know it. So let's go to hard fold handler. Let's go to definition of it. Okay. So it's not defined. Let me just see. Yeah, it's there here. Hard fold handler, nothing is written. NMI handler, nothing is written. PendSV handler, nothing is written. Similarly, all of them, nothing is written. But reset handler, I have written something. So always start any handler with proc and NP. Same rule applies. Okay. And once moment you write this export reset handler, so that you can call the reset handler from any place. If you don't write this, this will never work, because I'm calling reset handler here, it will never work. Okay. So always do that, export reset handler. Then import system init. It does something. And then import main. Okay. So import system init code and import main code. And main code is what you are writing in the main, right? Here, for example, here. Okay. The main is written. So now it makes sense. So first statement it does is CPSIDI. It is masking all interrupts. Of course, some interrupts are non-maskable, but this is just to do something, to do some system initialization, which is in this case only to enable the clock. It is masking all the interrupts. So let's do that. So, okay, so this is done. Is LDR R0 system init. So system init is a memory location. I can show 0x000111C is a location. So it is loading that address to R0 and then branching to that address. Let's now, you never observe this that carefully. So let's go this. So it is system init. It is written in C code. I have not started introducing the C code to you yet. I will have a separate session at some point. Maybe not part of the official lecture, but an extra lecture where I will introduce you to how to code everything in C rather than assembly language. It's much easier, but you should learn assembly thoroughly so that you know the essence of it. Okay. Here, system init is in C language. You can see it here. So basically, it is setting SIM register. Always remember our friend SIM. Okay, system integration module. COPC register, and it is setting to 0. All values are 0. Okay, let's go and see. It's not. You go back to the document of KL25 and then go to the system integration module, which is here. Okay, and then go to the memory map. And what was the register that you're looking at? SIM COPC. Okay, COPC. Where is COPC, our friend? Here. Okay, so you go here, you will see the COPC register. Okay, and COPC register, this is all hard coded. This is the only register that you should be. COPT, watchdog timer out, 0 is disabled. This is the guy, COP, 0 internal clock is enabled. If some bus clock you are providing, you have to put it as 1. So here I am putting everything as 0. That means the internal clock will start running. Yes, that's only thing that you're doing here. If you see that one more F, you're already at the end. I came back here. So this statement, system initialization, is only to actually enable the. So far you are blind. Previously, when you are running this code in lab, you are blind to it. Now you are really knowing it, what is happening. So this enables the clock. And now you enable black or unmask the interrupts. So it disable all the interrupts, set the clock, enable all the interrupts, whatever you have. Typically all interrupts are disabled, but some system interrupts by default are enabled. You are enabling it back. Now here again, you are loading the address of the main and branching to main. We are already here, and here is what I was telling. So the moment you press this button, in a typical hardware case, you should go and jump to this guy. But here, unfortunately, it will show an error here, that's all. You see it here, but it will not jump to here because it's no hardware here. Unfortunately, I cannot show. But I have manually written the hard fault interrupt handler, and whatever you want to write, you can write it over here. And whenever you see something like this, it comes here and executes this. Don't worry if you don't understand, because you have a lab associated with it, and we are also planning some simulation labs if possible. That may not be within this timetable till July 6th, but I will try to give it to you so that you can do it whenever you are free. And then when you come back over here, we will try to do it as most as possible. So that basically concludes. As I said at the start, if you have any questions, any doubts, please feel free to put your questions in the discussion forum so that everyone can see, and we will try to come back to you with the answer as soon as possible. Thanks for listening, and hope to see you in the next lecture.